Okay, so thanks everybody for coming. Today, our goal will be to discuss the continuous functional calculus in C-star algebras. Okay, so suppose that we have a Banach star algebra A, Banach star algebra, and suppose that little a is a normal element of A. So roughly, our goal will be to give a precise meaning to the expression f of A, where f is a continuous function defined on a compact subset K of the complex plane. Of course, if f is a polynomial, then f of A is already defined. Also, probably you know that if f is, for example, an exponential, the exponential function, then, well, f of A can be defined by a suitable power series. So what we want to do is to extend this expression to more general continuous functions, which are not necessarily given by convergent power series. So we suppose that K is a compact subset of the complex plane. And let little t denote the inclusion map of K into the complex plane. So T of lambda is lambda. By definition, a continuous functional calculus for A on K is a continuous unital star homomorphism. Which will be denoted by gamma A from the algebra of continuous functions on K to, oops, sorry. Just a moment. Okay, so gamma A is continuous unital star homomorphism from the algebra of continuous functions on K to A, which takes the function t defined above to our element A. Okay, sorry, but by the way, I forgot to say that A is assumed to be unital. So A is a unital Banach algebra, unital Banach star algebra. Okay, so this is the definition of continuous functional calculus. I would like to stress that the word continuous here refers not to the continuity of gamma, but to the fact that gamma is defined on the algebra of continuous functions. For example, if we replace the algebra of continuous functions by the algebra of holomorphic functions on an open subset of the complex plane, then we speak of holomorphic functional calculus. But today we are interested in the continuous functional calculus in the sense of this definition. Okay, so what can you say about this notion? First of all, we have the following simple result, proposition. If such a morphism gamma A exists, then it is unique. And the proof is very easy. We just observed that the subalgebra of C of k generated by the function which is identically 1, the function t, and the function t bar, where the bar is the complex conjugation. This subalgebra is dense in C of k by the Stone-Weierstrass theorem. So it's clearly a unital star subalgebra which separates the points of k. And that's it. Our gamma is unital, and since this subalgebra is dense, gamma is uniquely determined by gamma of t. But gamma of t is A. Now, this implies that such map is unique. A necessary condition for the existence of such map is given in terms of the spectrum of our element. And here's a necessary condition. If gamma A exists, then the compact set K contains the spectrum of our element A. And again, the proof is very easy. Indeed, suppose that gamma A exists. So sigma of A is sigma of gamma of F. But gamma is a unital homomorphism. And any unital homomorphism, a unital homomorphism doesn't increase the spectrum. So this is contained in the spectrum of F in the algebra C of K. Oh, sorry, F, not, well, A is gamma of T. A is gamma of T by definition, by the definition of gamma. So I try to replace here F by T. Oops. Never mind. So A is gamma of T. So this is necessarily contained in the spectrum of T in C of K. And the spectrum of continuous function is the set of values taken by this function. So this is T of K, which is just K. So we see that sigma of A is contained in K. And this completes the proof. Okay, now how about the existence of gamma? First of all, a useful exercise which shows that in general, the above condition is not sufficient. So construct a unital Banach star algebra A and a normal element sorry, something strange is happening. Okay, so construct A and the normal element little a such that the continuous functional calculus gamma A never exists. Whatever K, whatever the compact set K is. It turns out that if A is not just a Banach star algebra, but is a C-star algebra, then everything is okay. And the above necessary condition here is also sufficient. And before we prove it, let's introduce some notation. Suppose that A is a unit of C-star algebra, and S is a subset in A. We denote by C-star of S the intersection of all C-star subalgebras of A, all C-star subalgebras B of A, which contain S. So it's clear from this definition that C-star of S is a C-star subalgebra itself, because it's the intersection of a family of closed star subalgebras. And it is the smallest C-star subalgebra containing S. And we call it the C-star subalgebra generated by S. C-star subalgebra of A generated by S. This algebra can also be described explicitly. Namely, it's easy to observe that, first of all, C-star of S is, if S is any subset of A, then C-star of S is the closure of the linear span of all elements of the following form, so of all finite products A1 to AN, where each element AI is in S or is in S star, and N is an arbitrary natural number. Now, this is very easy because the right-hand side of this equality is easily seen to be a C-star subalgebra. And it is obviously the smallest C-star subalgebra containing S. And a special case, if little a is a normal element for our algebra, then the C-star subalgebra of A generated by A and the identity of A and the identity element is the closure of all elements of the form P of A star, where P runs over the algebra of polynomials in two variables. Well, this is immediate from the previous equality because each finite product of arbitrary number of copies A and star can be written as a monomial in A and A star because our element is assumed to be normal. And even a more special case, in particular, if A is self-adjoint, then the C-star subalgebra generated by A and the identity consists, well, this is the closure of all polynomials of A, P of A, where P runs over the algebra of polynomials over the polynomial algebra in one variable. Okay, now we have the following theorem about the existence of continuous functional calculus. Suppose that A is a unit of C-star algebra, and little a is a normal element of A. Little a is a normal element of A. I claim that for each compact subset K, well, just a moment again. I don't know what it is, but well, some strange activity of my tablet PC. I claim that for each compact subset K of the complex plane, such that K contains the spectrum of A, there exists a unique continuous functional calculus for A on K. And moreover, if K is exactly the spectrum of A, then gamma is an isometric star isomorphism of the algebra of continuous functions on the spectrum onto the C-star subalgebra of A generated by A and the identity element. Okay, let's now try to prove this result. First of all, let's observe that we may assume from the very beginning that K equals the spectrum. Well, indeed, if we constructed, assume for the moment that we have already constructed the functional calculus on the spectrum, then we can draw the following picture. So this is our functional calculus on the spectrum. If now K is a compact set containing the spectrum, we then have the restriction map from C of K to the algebra of continuous functions on the spectrum. And if we compose these two maps, then the result will be, again, a functional calculus for the same element defined on C of K. So we may assume from the very beginning that K is the spectrum. So let now B denote the C-star subalgebra of A generated by a little a and the identity element. Let's recall the spectral invariance result, which was proved at the previous lecture. So by the spectral invariance, the spectrum of little a calculated with respect to A is the same as the spectrum of little a calculated with respect to B. So we denote this simply by sigma of A. And consider a map phi from the maximal spectrum of the subalgebra B to sigma of A, defined by the following formula. So basically, this is the Gelfand transform of the element little a, but we interpret this element, this Gelfand transform, as a map from the maximal spectrum to sigma of A. By the way, of course, I forgot to say, but it's more or less clear from the definition that B is, of course, commutative, because A is normal element. So B is commutative. Okay, so what can I say about phi? Well, first of all, by the general properties of the Gelfand transform, phi is surjective. This follows from the basic properties of the Gelfand transform. I claim that phi is actually a homeomorphism. First of all, why is it injective? If phi of x1 equals phi of x2, where x1 and x2 are elements in the maximal spectrum of B, so we, as usual, we identify the maximal spectrum of B with the character space. B hat. So this means that this means that x1 of A equals x2 of A. Well, but we know that all characters over C-star algebra are star characters. And since x1 and x2 are star characters, this implies that they are the same on A star. Okay. But B is generated by A as a C-star subalgebra. So if x1 and x2 are the same on A and on A star, then they are the same everywhere. So this implies that x1 equals x2. So we see that phi is injective. I apologize for the strange behavior of my tablet PC. I don't know what is going on, but well, at the previous lecture I had a similar situation, but today it is essentially worse. Anyway, it seems that I can continue. Okay, so we see now that phi is injective. Phi is injective. And now the standard compactness argument implies that phi is a homeomorphism. That's because, well, the maximal spectrum is compact and sigma of A is Hausdorff. So we constructed a homomorphism between the maximal spectrum of B, where B is the C-star subalgebra generated by our normal element little a, and the spectrum of A. And by the way, this is the place where two different meanings of the word spectrum coincide. So the spectrum of the element A is homomorphic to the maximal spectrum of the subalgebra, of the C-star subalgebra generated by A. Okay, let's now look at the following picture. So our homomorphism phi determines an isometric star isomorphism between the algebra of continuous functions on sigma of A and the algebra of continuous functions on the maximal spectrum of B. So in the previous lecture, this isomorphism was denoted by phi dot. So phi dot takes each function little f to f composed with phi. And this is an isometric star isomorphism. Now the first Gelfand-Naimark theorem, which was proved at the previous lecture, gives us an isometric star isomorphism between B and the algebra of continuous functions on the maximal spectrum. Namely, the Gelfand transform of B is an isometric star isomorphism. So I can put here the inverse of the Gelfand transform of B, gamma B inverse, and this is also an isometric star isomorphism. And V is B, well, B is a C star subalgebra of A. So if we now compose all these arrows, what we get is a star homomorphism, gamma A, from the algebra of continuous functions on the spectrum to A. And I claim that this is exactly what we are looking for. Well, indeed, it follows from the construction that gamma A is a unital star homomorphism, a continuous unital star homomorphism. Also, since the first two arrows here are isometric isomorphisms, we conclude that gamma A is an isometric star isomorphism onto B. And now it remains to show that gamma takes T to A. So we want to prove this. We want to prove this equality. Well, this is equivalent to the following. Gamma V inverse phi dot of T equals A. Let's now apply gamma B to this equality. So this is equivalent to phi dot of T equals, and gamma of A is a hat. And by the definition of phi dot, this is T composed with phi. Well, but T is just the inclusion map from K into the complex plane. And if we look now at the definition of phi, we see that this formula is true. And so this implies that gamma of T equals A. And this completes the proof. So our map gamma is the continuous functional calculus for our elemental little a. Okay. Okay, let's now observe the following. Let's observe that if f is a polynomial in one variable, say x, and if we apply gamma to the restriction of a to k, then what we get is just f of a. Simply because, well, gamma takes t, the coordinate function t to a, so x goes to a, and f restricted to k goes to f of a. Just because gamma is an algebra homomorphism. More generally, the second observation, if we have a polynomial f in two variables, say x and y, let's introduce the following function f tilde. So we'll let f tilde denote the function from the complex plane to itself, given by the following formula. F tilde of z is f at z bar. Then it readily follows from the definition of the functional calculus. Then if we apply gamma a to the restriction of f tilde to k, then what we get is f evaluated at a and a star. Again, this follows from the algebraic properties of gamma. It is a star homomorphism. So it takes t to a and t bar to a star. And this observation justifies the following notation. For each continuous function f on the spectrum of A, we denote gamma of f simply by f of A. This is a very useful, a very convenient notation because, well, it is convenient, and second, it is compatible with the standard notation in the case where f is a polynomial. Okay, let's now look at some basic properties of the functional calculus. First of all, we have the following proposition, which is often called the spectral mapping theorem. Spectral mapping theorem. So for each continuous function n f on the spectrum of A, so as before, I assume that little a is a normal element in our unital C-star algebra. So for each continuous function f on the spectrum of the element f of A is the image of the spectrum under f. So the following nice formula holds. So we already know that this formula holds for each polynomial and for each element in an arbitrary unital algebra. And now we are going to show that the same formula holds for each continuous function. Well, okay. So what is sigma of f of A? Well, f of A is gamma of f. Let's now replace the C-star algebra A by the subalgebra B, where B is the same B as in the proof of the previous theorem. So B is the C-star subalgebra generated by A and the identity. So, well, the last equality follows from the spectral invariance result. And we already know that gamma is an isometric star isomorphism between the algebra of continuous functions on the spectrum and the subalgebra B. And since it is an isomorphism, we can continue this chain of equalities as follows. This is the spectrum of f calculated in the algebra of continuous functions on sigma of A. Well, but we know that the spectrum of a continuous function is the set of all values of this function, f of sigma of A. And this completes the proof. Another useful property of the functional calculus is the so-called superposition property. So suppose we have a continuous function f on the spectrum of A and a continuous function g on the spectrum of f of A. So we can now take g and apply it to f of A. And this is well defined because f of A is easily seen to be normal. Well, by the way, why is it normal? Well, f of A sits in the image of gamma, and gamma acts from a commutative algebra. So, of course, since all elements in the algebra of continuous functions are normal, it follows that f of A is also normal. So we can apply g to f of A. I claim that this is nothing but g composed with f applied to A. And again, I would like to stress that the right-hand side is well defined because of the spectral mapping theorem. So sigma of f of A equals f of sigma of A. So we can compose g and f. Okay, so why is it so? Let's consider the following map. Gamma from the algebra of continuous functions on sigma of f of A to A, given by the following formula. So what can I say about this map? It's clear from this formula that gamma is continuous unital star homomorphism. And it takes little t, whereas before little t is the inclusion of the respective set into the complex plane, to, well, what is this? This is, oh, sorry, I see a typo here. Of course, this is gamma of g, because f is already fixed, and g is a continuous function on sigma of f of A. So gamma of g is g composed with f applied to A. So what is gamma of t? Well, this is t composed with f and applied to A. Of course, t composed with f is just f, so this is f of A. And now by the uniqueness of the functional calculus, we conclude that gamma is nothing but the continuous functional calculus for the element f of A. And that's it. This formula is equivalent to g of f of A equals g composed with f and applied to A. And this completes the proof of the superposition property. Okay, a little problem with this construction with the functional calculus is that our element little f of A is not given by any explicit formula. And the reason for that is more or less clear. When we constructed the functional calculus, we applied the map, which is the inverse, to the Gelfand transform. the inverse of the Gelfand transform is quite unexplicit. And this is the reason why we don't have a convenient formula for f of a in the general case. Unfortunately, in some special cases, such an explicit formula exists. And here are two exercises. So two special cases in which we have an explicit formula for a functional calculus. First of all, suppose that A is suppose that A is the algebra of continuous functions on a compact Hausdorff topological space. I claim that for each element A in our algebra, and for each continuous function f on the spectrum, f of A is sorry. Okay, sorry. So f of A is just f composed with A. F composed with A. So A is a function on X. F is a function on sigma of A, which is A of X. So we just compose them. And this is the explicit formula for the functional calculus. And another exercise, which is maybe even more important. Suppose that we have a measure space, X mu, measure space. And let phi be an essentially bounded measurable function on X. And consider the multiplication operator m phi, which acts on the space L2 of X mu to itself. So this is just the pointwise multiplication by phi. This is one of the most classical and useful and important examples of a normal operator on a Hilbert space. So I claim, and this is an exercise, that f applied to m phi, the continuous functional calculus for the multiplication operator, is given by the following explicit formula. This is the multiplication operator by f composed with phi. So here f is a continuous function on the spectrum of m phi. Also, I'd like to stress that to prove this formula, we must also show that f composed with phi is well defined. Because, well, the spectrum of m phi is not precisely the set of values of phi. It is you may remember that this is the set of essential values of phi. So before proving this formula, we must explain that this composition is well defined. Okay. Let's now continue to study some general properties of the functional calculus. Our next goal will be to show that the functional calculus is continuous as a function of two variables. So far we know that, of course, it is if we fix little a, then the map which takes f to f of a is continuous. So now we want to show that it is continuous as a map as a function of two variables, little f and little a. Before we can do it, let's recall some definitions from general topology. Suppose that X is a topological space, and suppose that Y is a subset of X. We say that Y is locally closed in X if Y is an open subset of its closure. Well, here's a couple of simple examples. Let's observe that a closed subset is clearly locally closed. And second, it's also clear that each open set is locally closed. Well, indeed, if Y is open, then it is open already in X, and moreover, it is open in its closure. Well, actually, it's rather easy to show that it's simple exercise to show that a subset is locally closed, if and only if it is the intersection of an open set and a closed set. And also, it's rather easy to prove, to give a local characterization of locally closed sets. Well, maybe I'll not explain this now because we will not need it. What we actually need is the following simple but useful observation. So let's also observe that if X is locally compact and Hausdorff, and Y is a locally closed subset of A, then Y is also locally compact. This readily follows from the fact that a closed subset of a locally compact space is locally compact, and an open subset of Hausdorff locally compact space is also locally compact. So if Y is locally closed, we see that Y bar, the closure of Y, is locally closed, and the closure of Y is locally compact, and Y is also locally compact because it is an open subset of its closure. We now have the following result. Oh, sorry, before I formulate the theorem, I need some more notation. So some more notation. Suppose now that A is a unit of C-star algebra. Unit of C-star algebra. And suppose that Y is a subset of the complex plane. we denote by A norm of Y the set of all normal elements in our algebra such that the spectrum of A is contained in Y. And the set of all normal elements of A will be denoted just by A norm. We now have the following result, the theorem. So consider the following map from C of Y. Oh, sorry, I forgot to say what Y is. So I suppose that Y is a locally closed subset of the complex plane. So suppose that Y is a locally closed subset of the complex plane. Then the map from the product of C of Y and A norm of Y to A norm, which takes each pair F and A to F of A is continuous. Is continuous. So here, C of Y is the algebra of continuous functions on Y, and it is equipped with the standard topology of compact convergence, the compact open topology. And here's the proof. First of all, as before, for each polynomial P in two variables, sorry, I'd like to choose so before I do it, let's prove two auxiliary lemmas. This will be more convenient. Instead of incorporating the proofs of the lemmas to the proof of the theorem, I prefer to prove them separately. Well, lemma 1. Lemma 1. Suppose that A is a unital Banach algebra. A unital Banach algebra. And little a is an invertible element of A. Then for each element B of our algebra, such that the norm of B is strictly smaller than Y, strictly smaller than Y divided by the norm of A inverse, the element A minus B is invertible. The proof is very easy. We just observe that A minus B is A multiplied by 1 minus A inverse B. And that the norm of A inverse B is strictly smaller than 1. And that's it. So we know that since the norm of this element is strictly smaller than 1, this element here in brackets is invertible. Also, A is invertible. And the product of two invertible elements is invertible. And this completes the proof. And one more lemma, lemma 2. In some sense, this lemma will show that the spectrum is semi-continuous. Semi-continuity of the spectrum. Can you hear my kids?
Yes, we can.
I'm sorry. Let's see. Okay, so again, A is a unit of Banach algebra. A is a unit of Banach algebra, and little a is an element in A. And suppose that U is an open subset of the complex plane, which contains the spectrum of A. I claim that there exists a neighborhood V of A in our algebra, such that for each element B in V, the spectrum of B is contained in U. So in some sense, this lemma means that the spectrum is semi-continuous in the sense that if B is closed to A, then the spectrum of B cannot be essentially bigger than the spectrum of A. Theoretically, it can be essentially smaller. Well, it is contained in U, and it can be essentially smaller than the spectrum of A, but it cannot be essentially bigger. So this is the informal meaning of this result. And here's the proof. We let C denote the supremum of the resolvent function of A over the complement of U. Let's recall that this function, which takes lambda to A minus lambda inverse, this is the so-called resolvent function of the element A. This function is continuous at the complement of the spectrum, and it vanishes at infinity. And this easily implies that C is finite. If we now take an element B in our algebra A, such that B minus A is smaller than 1 divided by C, if we take any point lambda, which is not in U, then, well, I claim that B minus lambda is invertible. To see this, we write this element as follows. This is B minus A. Oh, sorry. It would be more convenient to start with A minus lambda. So this is A minus lambda plus B minus A. Okay, so A minus lambda is invertible because lambda is not in U, and moreover, it is not in the spectrum of A. And the norm of B minus A, the norm of B minus A is less than 1 over C. And by the definition of C, this is less than or equal to the norm of A minus lambda inverse. And if you now apply lemma 1 to these two elements, we conclude that B minus lambda 1 is invertible. And since lambda was an arbitrary point in the complement of U, this implies that the spectrum of B is contained in U. So we see that the neighborhood V we are looking for is just the open ball with center A and of radius 1 over C. So this completes the proof. Okay, now we're ready to prove our theorem. So this is the result we are going to prove. Let's call this theorem the joint continuity property, the joint continuity of the functional calculus. Okay, so first of all, let's take polynomial P into variables, X and Y, and so we use the same notation which was introduced a little bit earlier. We let P tilde denote the function from the complex plane to itself, given by the following formula. So P tilde of Z is P of Z and Z bar. And let's observe that the map from a norm to itself which takes each element A, each normal element A to P tilde of A is continuous. Well, this is more or less clear because, well, this is a finite sum of monomials in A and in A star, and each monomial is a continuous function. And the sum of finitely many continuous functions is continuous. Okay, so let now A0 be an element in A norm of Y. So this is normal element whose spectrum is contained in our subset Y. Let F0 be a continuous function on Y. And let epsilon be an arbitrary positive number. So we have to show that if F is close enough to F0 in the topology of C of Y, and if little a is close enough to A0, then F of A is close to F0 applied to A0. So this will show that our map is continuous. Okay, first of all, we look at the spectrum of A0, and we recall that Y, since Y is locally closed, it is locally compact. And since it is locally compact, there exists an open set U in Y. I mean, open in Y, open in the induced topology. It is not necessarily open in the complex plane. It is open in Y, such that sigma Y is contained in U, and such that the closure of U in Y is compact. Well, actually, this is a little exercise. There is a little exercise here. Well, by the very definition of locally compact space, each point in Y has a neighborhood whose closure is compact. But the standard compactness argument shows that for each compact subset of Y, there is a neighborhood of this subset whose closure is compact. So we know that such U exists. Okay, now we apply, sorry, this should be sigma of A0, A0. We now apply our lemma 2. So by lemma 2, there is a neighborhood V of A0 in R algebra A, such that for each element little a in this neighborhood, the spectrum of little a is also contained in U. Okay, let's now choose a suitable polynomial. We choose a polynomial P in two variables, such that P is uniformly close to F0. Not exactly P, but P tilde is uniformly close to F0 over the closure of U. So I mean that we choose it in such a way that this norm is smaller than epsilon. We can always do it because the set of all polynomials in Z and Z bar is dense in C of U bar by the Stone-Weierstrass theorem. Also, without loss of generality, we may assume that for each element A in V, well, for each normal element A in V, P tilde of A is close to P tilde of A0. Well, indeed, P tilde is continuous. So by taking maybe a smaller neighborhood than V, we can always achieve this inequality. So we just we don't want to introduce new notation, and we may assume from the very beginning that this holds for each element in V, or each normal element in V. Oh, I'm sorry. I would like to come back once again to this formula. Formally, this is not entirely correct because U is not necessarily open in the complex plane. So let me repair this part of the proof. Well, U is open in Y, and so we can write U in the following form: U is in the intersection of Y and W, where W is open in the complex plane. And now we apply our lemma 2, but not to U, but to W, which is open in the complex plane. Okay, now this is correct. Okay, and let's now compare f of a and f0 of a0. So we take any continuous function f on y, c of y, such that f is uniformly close to f0 on the closure of U, and take an element A in the intersection of V and a norm of Y. And let's compare f of A and f0 of a0. Well, this can be evaluated as follows. This is less than or equal to f of a minus f of a0 plus oh no, sorry, so this is less than or equal to f of a minus minus f0a plus f0a minus p of a, p tilde of a, plus p tilde of a minus p tilde of a0, and plus p tilde of a0 minus f0 of a0. And let's now look at each summand separately. Well, the first summand can be evaluated as follows. The spectrum of A is contained in U bar, and f minus f0 is smaller than epsilon over U bar. So by the properties of the functional calculus, this is smaller than epsilon. For the same reason, the second summand is smaller than epsilon because of this. Because f0 and p tilde are uniformly closed in C of U bar. The third summand is smaller than epsilon because of this. And finally, the fourth summand is smaller than epsilon for the same reason. So p tilde, for the same reason as the first summand is smaller than epsilon. So p tilde minus f0 is smaller than epsilon over U, and by the properties of the functional calculus, this is smaller than epsilon. So that's it. We conclude that the sum of all these four summands is smaller than 4 epsilon. And this completes the proof, because we have found a neighborhood of f0 in C of y. So this inequality determines a neighborhood of f0, and we have found a neighborhood of A of A0 in A norm of y, such that our map takes the product of this neighborhood and this neighborhood to a neighborhood to a ball centered around f0 of A0 of radius 4 epsilon. So this implies that our map is continuous. So this completes the proof. Okay, and so it's time to finish. So that's all for today. And at the next lecture, we discuss positive elements of C-star algebras, and in particular, positive operators on the Hilbert space. And then begin to discuss the so-called polar decomposition of linear operators on the Hilbert space.